Hello everybody. This week's lab is going to be largely review. We've covered pretty much all the big ideas already in density in the videos last week. But there are a couple of hints that I want to give you guys to be a little bit more successful on this quiz. So first I want to talk about glassware and why there's different kinds of glassware that we use in chemistry, and what the advantages and disadvantages of them might be. They're all very specifically made in order to achieve different things. So the first one we have our beaker, and this is just pretty much our workhorse. You're going to use a beaker just like you basically would a cup. It's just a handy tool. It's easy to pour into from a larger container. It can be easy to pour out of. It usually has like a little divot thing right here that makes it so that it pours nicely out of it, and it's got some graduations on them, but they're not really very accurate at all. They're only for approximate amounts, so you can't make very careful measurements with it, but it's very convenient for transferring approximate amounts from one container to another. The next one would be the Conical or the Erlenmeyer flask. And basically this is a beaker that is narrowed around the top. And the narrowing does exactly what you might think that it would. It makes it so it's a little harder for things to come out. Right? So if I'm stirring this solution, then it's not going to want to splash out like it might with a beaker. But another thing that you guys might not be aware of is this idea of reflux. So one of the big things we're going to do in chemistry is produce solutions and then heat them. And when you heat them, it will evaporate. If you've ever cooked, you'll know that you lose volume and it leaves the container. By making this a little bit narrower here, what we can do is kind of prevent it from leaving. So it would rise up and it's going to hit this wall of the container. It's going to be quite a bit cooler because it's not in contact with the hot liquid. And then it's going to condense on there, and then it's going to slide down the outside and back into the solution. Only a smaller amount is going to be able to be right in line with the mouth of the container and be able to leave. And so we can kind of keep our solution in here a little bit more without having to add more all the time. Also, we keep the bottom quite wide, and that's because if I set this on a heat source, I still have a very wide, large area that's in contact with the heat source. So I'm getting good heat transfer between my heat source and the solution. Next, we have graduated cylinders, and these are going to have well-defined graduations. So there's going to be a lot of graduations, and they're going to be a lot more accurate than one that you would find on, say, a Erlenmeyer or a Beaker. One of the big problems with the Beaker and the Erlenmeyer is they're too wide to clearly see the meniscus. Okay, the meniscus becomes much more pronounced as the container gets narrower, and so that makes it a little bit easier to figure out where the bottom of the meniscus is in order to get that very accurate reading that we need and take advantage of all those graduations. And I'm going to save you guys the mathematical derivation, but I could show you that mathematically the narrow radius makes it intrinsically more accurate to measure a height and convert that over to a volume. And finally, I'm going to introduce a very specialized piece of glassware. It's probably the most accurate kind of glassware that you're going to find to deliver a volume. And it has a very specialized shape that I like. So I want to point this out to you guys. This is called a volumetric pipette. It's only going to have one graduation, so it only delivers one volume, right? It's set to deliver just that volume. This is very carefully calibrated. by the manufacturer. And what it does is it has this bulb here, and the reason being they want this to be very narrow because that's going to be accurate, okay? But if I wanted it to hold a bunch of volume or any real significant volume, it would get very, very long. It would be very difficult to draw all the solution up into it. So they add this bulb so that it can hold the majority of the volume, and while keeping the spot where we're going to make the measurement very, very narrow. And the final thing is that there's always this great conundrum when that students realize really quickly when they're trying to make accurate volume measurements, and that is I can put so much volume in here, but I can never get that to go over to another container all the way. There's always a little bit kind of clinging in here somewhere, right? And this is actually calibrated to allow for that. What's going to happen is you're going to fill it up to here. You're going to allow it to drain down. It's going to wick down very slowly, which is going to allow time for all the little droplets to coalesce and come down. You're not going to see a lot clinging to the inside here. And then when it gets down here, there's going to be a predictable volume that always remains in the tip here. And so the manufacturer is going to set this mark to allow for this little bit to be left down in here and to deliver the amount that it's supposed to while actually holding a little bit more. The other little hints that I need to give you guys for this quiz are about best practices when making measurements. So whenever possible, you should always use the smallest glassware that will fit the volume you are working with. So if you're going to measure out 7 mils and you have the option between a 10 and a 25 mil graduated cylinder, you want to use the 10. And you're going to notice that these smaller ones are often going to have graduations that are smaller themselves. So each little graduation is going to represent a smaller unit, and you get more precise measurements from that. The last thing I want to mention is the connection between the last significant digit in a mass measurement and the tolerance for a balance. So the tolerance tells you that if I measure out 15.01 grams, that's 15.01 grams plus or minus a maximum of 0.01 grams. So if it says 15.01, it could be 15.00, it could be 15.02, it could be any value in between those two. So you can see here that the last tolerance is in the hundredths place and the last part of our measurement is in the hundredths place. Similarly here we have the tenths place for a balance with the tolerance in the tenths place, and then to go all the way out to the thousandths place we need a balance with the tolerance out to the thousandths place.